Hey, welcome back to our series of math videos. Today we get to solve equations. Specifically, we'll look at determining whether a given number is a solution. We'll look at the addition and multiplication principles and also put those principles together and look at some special case kind of equations to solve. So equations are, I guess, the equality of two expressions. And a solution to any equation are all those values that make the statement true. When you look at this particular equation, you might be able to look and just say in your head what the answer would be. But we'll look in this video at ways that I can solve that. One thing I can do first, though, is I can determine whether if they give me answers or possible answers, I can determine whether those answers are true or not. And I can determine that by plugging a 2 in everywhere I see an x and see if the two expressions are equal to each other. Let's try that. Here's my equation, and I'm going to determine whether 2 is the answer or not. So everywhere I see an x, I'm going to put in a 2. Notice I use brackets there. That's always a good practice to put brackets in when you're substituting in for a variable. Okay, so 2 times 2 is 4, and 4 plus 4 plus 4 is 8. It's not equal to 10. Since this is a false statement, 8 can't be equal to 10, therefore 2 is not a solution. So therefore 2 is not a solution. And I could go ahead and in the question ask us to see whether 3 was or whether 4 was. You can probably see in your mind 2 times 3 is 6, 6 plus 4 is 10, 3 would be the correct answer, 4 wouldn't work. Sometimes we have two numbers that might work, or 3 or 4 or more than that. And we'll see how we can solve equations to see how many solutions I could get. So let's look at the addition principle. The addition principle, like the multiplication principle, says that if I add something on one side, I have to add it to the other side. And if I do that, then the equality of the two expressions remains the same, or the two expressions remain equal. So in this case here, I have x minus 3 is equal to 12. When I solve any equation, that's what we're doing, I want to see what x is equal to. So currently in this equation, I have x minus 3 is equal to 12. Well, I don't want that 3 in there. I just want x is equal to. So I want to get rid of this minus 3. To do that, I can use the addition principle. So on the left side, I'm going to add 3. But if I add 3 on the left side, I also have to add 3 on the right side. So notice in red, it's the same as the original equation. And I've added 3 to both sides. That's the addition principle. If I do it to both sides, the quality of the equation remains. So now, to solve the equation, a negative 3 plus 3 is equal to 0. That's why I added 3, was so I could get rid of that. So on the left side, I only have x. Now on the right side, 12 plus 3 is 15. So now, like I said originally, I wanted x is equal to something. I have an answer. Always when you're solving equations, a good practice to do is to check your answer. So I say my answer is 15. Let's plug 15 in there and see if it works. I'll rewrite the equation, and instead of the x, I'm going to put in what I think the x should be, a 15. And I'm going to see whether that is true. And you can see that 15 minus 3 is 12. And 12 is equal to 12. Therefore, 15 was a correct answer. Here's another example of using the addition principle. This time, notice that there's an add 4 here. So if I want to get rid of that, so if I have x plus 4, to get rid of it, I can subtract 4. Or I can add a negative 4. Typically, that's why we still can call it the addition principle. Typically, we just say subtract 4, but you could have said add a negative 4 there as well. So it's equal to 8, and on this side I subtract 4 as well. So 4 take away 4 is 0, so on the left side I'm left with x, 8 take away 4 is 4. Again, if I go back and check, 4 plus 4, oh, this says negative 8. Isn't that good, eh? I didn't do that on purpose, but it's given me a chance to talk about checking. I went back and 4 plus 4 is equal to 8, not a negative 8. So I did something wrong in here. So if I look back, I see, oh, I forgot to write this as a negative 8 there. So negative 8 take away 4 isn't a positive 4. Negative 8 take away 4 is actually a negative 12. Oh, phew. So I missed my negative. Happens to the best of us. Now when I go back and check, negative 12 plus 4 is indeed a negative 8, so my answer is correct. So that's the addition principle. Here's a couple of questions for you to try. Notice I upped the ante a little bit, threw some decimals and some fractions in there a little bit. Okay, so press pause and try these ones on your own, and then press play for the answers. This question here, I would add 1.5 to both sides. So I have negative 12 plus 1.5. Notice I skipped a step there, I just did it in my head. Negative 12 plus 1.5 would be negative 10.5. On this side, I have to subtract 2/3 on either side. So subtract 2/3. I need to get a common denominator with these fractions. I'll show you in a second here how another way of dealing with these fractions, but I'll just get my common denominator. So that'd be 15, so it'd be negative 9/15 subtract 10/15. So my answer to this one would be negative 19/15. And I could go back and check that one. Ooh, checking with fractions. I might try my calculator on that one. But you could do that. Okay, the multiplication principle, same thing as the addition principle, except this time I'm multiplying x by a value, so I want to get rid of this 5 because I only want x is equal to. So I have to get rid of the 5. So if it's 5 times x, which is what this is, I can divide both sides by 5. I like to write it in another step rather than writing divide by 5 right off the bat here, just so I don't mess up the original question. So I'm going to take on the left side divide by 5 and divide by 5 on the right side. So here 5 divided by 5 is 1, so I'm left with 1x, and 12 divided by 5 is 12/5. Done. Again, I could plug that back in to check it. Let me erase that, and I'll check this one. 5 times whatever x is, 12/5 I'm saying, is equal to 12. 5 divided 5 is 1, so 1 times 12 is 12. 12 is equal to 12. My answer checks out. This one here, in this case, I'm dividing by 3. So in order to get rid of the divide by 3, I'm going to take and multiply both sides by 3. So instead of dividing by 3, I'm going to take and multiply this side by 3. And if I do that, I need to multiply the other side by 3. 3 divided 3 is 1, so I'm left with an x. 20 times 3 is 60. Again, I can check. 60 divided by 3 is 20, so my answer checks out. Here's a couple more. Try these ones on your own. Press pause, try them, check back when you're done. I'll divide both sides by negative 3 in this case, and 3 into 42 I think goes 14 times, so x is equal to negative 14. And I could go back and check negative times a negative is positive, 3/14 so 42 checks out. In this case here it's a little different. I've got negative 3/7 times y is equal to 21. If I wanted to, I could say I'm multiplying by y by a fraction. Or I could say I'm multiplying by 3 and dividing by 7. So I could apply the rule twice or once. I'm just going to apply it once. So minus 3/7 times y is equal to 21. So what I want to do is I want to divide this side by negative 3/7. That will cancel these out, or these will divide evenly, and I'll be left with 1y here. And then on the other side, I'll also divide by negative 3/7. Notice that I wrote it a different way. It's the same thing I'm dividing. This means divide, this means divide. But in this case over here, you're probably immediately thinking, oh, right. When you divide fractions, I can multiply by the reciprocal. So it'd be 7 over negative 3. So 3 goes into 21 7 times. 7 times 7 is 49, and it's negative 49. So my answer is negative 49. Okay, so these are different applications of the multiplication principle. Now, putting them all together, sometimes I'll have to use the addition principle and the multiplication principle in the same question. Typically, what we do is we use the addition principle first, or in other words, get your like terms together. Then, at the end, use either the multiplication, or I guess we could call it the division principle. So in this case here, I'm adding 8. I'm going to subtract 8 from both sides. So I'll have 5x is equal to negative 115. Now I'll use the division principle and divide both sides by 5. So 5 goes into there, negative 2 and 3. So negative 23. I could plug that back in and check, and I should do that, check to see if my answer is correct. In this case here, I'm going to add 4 to both sides. So 9t is equal to negative 108, and then divide both sides by 9. 9 will go into this, negative 12. And again, I should check to see if that is correct. So you see how we use the addition principle first. So I subtracted 8 from both sides. Notice I did that in my head rather than writing it down. If you find yourself making a mistake or two, write that extra step in. Same thing here, I added 4 to both sides and then divided both sides by 9. Now sometimes if I have fractions or decimals, there's a couple of little tricks that I can use to get rid of those. They might look a little bit messy, but what they do is they make it so you don't have to deal with fractions or decimals. In the case of fractions, look for a common denominator and multiply each term by that denominator. In this case, my lowest common denominator is 6, so I'm going to multiply each term by 6. So I'm going to take the 2/3. I'll just write the whole thing out again. Minus 5/6 y is equal to 1/3. So I'm going to take the 2/3 and multiply it by 6. I'm going to take the minus 5/6 and multiply it by 6. Whoops. And take the 1/3 and multiply it by 6. It looks a little bit ugly, but watch what we get at the end. 6 times 2 is 12, divide 3 is 4. Notice no fraction. Minus 6 5s are 30, divide 6 is 5, so I get 5y is equal to 6 divided by 3 is 2. Suddenly I have an equation that doesn't have any fractions. Now I can go ahead and solve that using addition principles, multiplication principles, etc. I won't, I just wanted to show you this part here. Similarly, when we deal with decimals, I can do the same thing. Here I've got decimals where I have 2 decimals here, 2 decimals there, 2 decimals there. If I have 2 decimals, what I can do is take and multiply every term in the equation by 100. Notice there's 2 zeros. So 100 times 0.10 would be 10x, plus 100 times 0.34 is 34, and 100 times 0.54 is 54. Notice right away there I've taken the edge off of the question. I've taken it from being a decimal question where I'm just a little bit hedgy into a question where all I have are integers, and this one would be simple to solve. 10x, 34 subtract on this side would be equal to 20, divide both sides by 10, I get x is equal to 2. Okay, so dealing with fractions and decimals, these are I guess 2 methods that I can use to make my questions just a little bit easier. If I wanted to keep the question in fractions, keep the question in decimals and solve, as long as you follow the proper principles, you'll still solve and get the same answers. Okay, we talked earlier about sometimes you might not get an answer, and here's a couple of questions where they're just a little bit different, but I just wanted to show you what happens with them. In this question here, say I've got 3x plus 9 equals 3x minus 5. Let's collect the like terms together. So I'm going to subtract 9 on both sides, so I'll get 3x is equal to 3x, and minus 5 minus 9 is minus 14. I'm going to move the 3x over to this side, so I'll subtract 3x on both sides. So I'll have 3x minus 3x is equal to negative 14. 3x minus 3x is 0. Hold on, that's a little funny. Is equal to negative 14. I'm getting into some territory I might not have seen before. So here actually the x terms cancel out, and I came out with a statement that says, or an equation that says 0 is equal to negative 14. Well, I know that that's not true, like 0 is not equal to negative 14. Therefore, when I look back here, what I'm trying to do is find a number that plugs in for x to make this statement true. If I come up with a false statement like this, that means that there's no solution. There's no number that I can get to plug in for x that would make this equation true. Conversely, here's a question where notice that there's similar things on both sides, and some of the ones in your homework may not look exactly the same. But watch what I get to happen here. I'm going to add 5 to both sides, so I'm going to get negative 10x is equal to, if I add 5 to this side, minus 5 plus 5 is 0, so I just have minus 10x on this side. Well, that's looking a little funny too, isn't it? Let me divide both sides by negative 10, and I'll get x is equal to x. That seems a little bit funny. If I get a statement like this where I get x is equal to x, or if I get something like 4 is equal to 4, which I know is a true statement, then what happens is that all real numbers are solutions. Meaning I can plug anything I want in for x, and this statement or this equation would be true. Okay, finally, last concept. Just a couple things for you to follow when you're solving equations. First, I would try and clear all fractions or decimals using that method that I showed you here a slide or two ago. Then clear any grouping symbols like brackets that you might have there. Then use the addition principle to collect like terms, isolate the variable, and finally use the multiplication principle to finish the question. Here's a question where I'll do that. I see brackets first. Well, I don't see any fractions or decimals, so I'll move past that. I see brackets, so I'm going to multiply that through. So 3x plus, this will be 8x. 8 times 2 is plus 16, is equal to 11 plus 7x. Okay, I've got rid of my brackets. Now I want to use the addition principle to collect things that are the same. Let's get all the x's on the left side and all the numbers on the right side. So I have 3x plus 8x, that's 11x. I'm going to subtract 16 from both sides. So this will be equal to 11 plus 7x minus 16. Okay, so I have 11 minus 16. Those are like terms. That's minus 5 plus 7x. I know you're anxious for me to get that 7x over there. I'll do that now. I'll subtract 7x from both sides. So 11x minus 7x is 4x. Is equal to negative 5. And then I'll divide both sides by 4. So x is equal to negative 5 over 4. So this would be my solution to that equation up there. In order for this equation to be true, for this side to be equal to that side, the x value I need to plug in is negative 5/4. And I could plug that in and check to see if my answer is correct. So in this section, we've looked at seeing whether a number was a solution to an equation. We've looked at combinations of addition and multiplication principles. And we've also looked at different kinds of equations where I might come up with a false statement or no solution, or a true statement meaning all numbers are solutions. These are good questions to practice lots and lots of. If your instructor tells you to do every other odd question, you might want to do a few more than that, just to give you lots of questions under your belt. Practice, practice, practice. Ask your instructor if you have any questions. Okay, see you next time.